Okay, so I think we will begin as soon as we reach 50 participants. Okay, let's begin. So last time we talked about the TCP congestion control, right? Because in a prior slide we talked about the, flow control. But flow control, the window is only controlling the sending speed to match that of the receiver. Okay, but because TCP is a transport layer, it has no access to the network layer, right? It only knows what is up there, not down there. Okay, so it has to do congestion control in a way that is end-to-end. Right? So what you can do is you detect the packet loss, and if there's a packet loss, then you can. Let me see the chat. Oh, sorry. So yeah, I thought yeah, it is just. Are you seeing the right screen now? Okay, thank you. Thank you for the reminder. Yeah, so the congestion means that there's a bottleneck link, right? And so you are sending too fast, and you will have packet loss. Okay, and TCP basically is like a courtesy by everyone, right? So if you detect any packet loss, what you will do is that you will back off, right? So we talked about the if you are in the cliff, then continuous sending will just make things worse. Right? But everyone should be fair and follow the same protocol, which means, let me see. We will do this one, okay? We'll do this one, right? So this is called an additive increase, right? When you increase linearly, right? Whenever you get acknowledgement, you increase the window a little bit, okay? But if you, you find, hey, there's a packet loss, right? So what do? You kind of reduce the window, right, significantly. It's called a multiplicative decrease, okay? Right, and only this scheme, we looked at 4 schemes, only this scheme has a guarantee of fairness, right? Because whenever you are, if you keep adjusting like this, right, you find a congestion, you adjust congestion, you will reach a very fair condition. I hope you still remember the analysis we went through last time. And the implementation of congestion control, we have three parameters. One is called advertised window, which was the window that is in the TCP header when you receive maybe some message from the receiver, right? And so the congestion window, C window, the congestion window, is a window that you are currently detecting the congestions, okay? Right. So you should have a small of those windows, right? Because you cannot go beyond either one, okay? This is the actual window size. And additionally, one important thing is called the SS threshold, right? So SS means slow start, right? And last time we have seen an animation showing that slow start is just a name, right? So actually it's exponential, right? It doubles the window size each time, okay? And after this threshold, right? So you should then be conservative, right? So you should additive increase instead of multiplicative increase, right? But when you detect the congestion, you should do a multiplicative decrease, right? So this is basically what the TCP protocol is about. Okay. So in the slow start stage, what you do is whenever you get an acknowledgement, right, you add the window size by 1. Okay. And last time we see is the animation here, which show that it actually doubles the window after each round trip. Okay. This can continue until, let's say, you go beyond the SS threshold, right? So this is one way. Okay. Another way is maybe your SS threshold is too high, then you will detect a packet drop, right? So which means it's already congestion is already happening, okay? And then you also, stop this, okay? And after you go beyond the SS threshold, you will reach another stage, which is called the congestion avoidance, right? Instead of whenever you get an ACK, you increase your window size by 1. Now you should increase 1 divided by the current window size, okay? And we explained why this works, right? So after you get to 8, right, so which is here, then what you should do is you should increase linearly, right? So you add, you add slowly, right? For example, when this gets back, you add 1 by 8, okay? Because it's 8, okay? After you add 8, 1 by 8, you increase to 9, okay? Next time, next round trip time, you increase by 1, right, on both sides, okay? You have 1 round trip, right, this access. and you also increase the window by 1. Okay, you should not double. Okay, you double, probably congestion happens very quickly. Okay? So the first stage, which actually doubles each time, is called a slow start. But after that, you have, after the slow start threshold, you should increase the limit. Right? So let's look at the pseudocode. Right? So the pseudocode is something like this. This is how you understand in more rigid way. Right? So firstly, you have the window size initially always 1. Right? So like here. Okay. And then you should have a threshold. Right? So you think about it, initially, you still should have a threshold where you should stop the slow start. Okay. So how to do that, right? So right now I don't have any other information, right? But I know that I cannot go beyond the advertised window from the receiver. Right? So initially you will set the SS threshold to be the advertised window size, okay? And then you will start to get an acknowledgement after send stuff, right? So, and if your threshold is less than the SS threshold, you will add by 1, okay? After each command. And if you otherwise, right? So you will add 1 divided by your current window size, okay? Because each round trip time you will get so many packets that you send out for the whole window, right? So this is called congestion avoidance, right? And here we are using, it's not so accurate, frankly speaking. Right? So this is the 1 by, 1 by 8, then probably 1 by 9, 1 by 10, right? But approximately it's a linear, right? So, okay. And then you will have a timeout, right? So this is when you have really the packet loss, right? So this is increasing because you get acknowledgement. But then if you don't get an acknowledgement, right, you find a timeout, which means you don't get an acknowledgement in time, potentially that the packet loss. So what you have is you will, so this is the key. Okay, so let me highlight this. Okay, so this, so yeah, student may get confused here. So what you do is your window size is not cut by half. Your window size go to 1, okay? Go to 1 again. But again, this is the very basic form of TCP, okay? So your window size go back to 1, right? It's not even, right, when you detect congestion, when your window size is maybe 64, you not go to 32, go to 1. Right? What is cut by half is actually something like the SS threshold, right? Previously, you have a threshold. Now, potentially, this threshold, if you keep the old threshold, it's not good. Right? You aggressively decrease the threshold. Okay, so there's still a stage where you need to restart the window and do a slow start until you reach here. Okay, right. And the reason is because if you detect congestion here, right? So this is definitely not safe. But you play safe. You say, hey, here it should be safe, right? Unless things really change quickly. Okay, then you can quickly double to here, and then you slowly probe. Because you don't know where you fail, right? And so you potentially here you fail, but you already go beyond it because there's some delay, right? And timeout, if you remember, okay? Twice the launch time, okay? So you probably will probe slowly, and this will fluctuate dynamically, right? So, but here it's pretty safe. You assume you quickly go to here, okay? But your window is 1, okay? But you just quickly go to the threshold, okay? Which is cut by half. All right, so if this is clear, let's take a look at the animation, right? So then if you don't understand this animation, just let me know. Okay, so first let's assume the initial threshold is advertised window from the receiver, right? So you will do slow start, okay? And you can go all the way up, right? So, but unfortunately, your congestion level is high, right? So you cannot really go to the advertised window. Then there's a timeout happen. Remember, there's some time. Right? This timeout is twice the round trip time. Okay, so that definitely has a horizontal line around the time. Okay, after that, if you look at here, the window size go back to 1. Okay, it's not a half. Okay? But you will quickly come back. Okay, this time you come back at your previous window reach here. Right? Your S threshold now is you see the dotted line now become half of your previous peak, okay? And then you can quickly increase here, but then you should slowly increase because you don't know, it's close to here, there's congestion, right? You can only safely, slowly increase till where it is here, okay? Right? Especially this may be frustrating. Yes. select trade, okay? And then somehow, there's even more congestion. Here you time out, right? So you should go back to 0 again and quickly start to this half, right? You see the window size keep decreasing if there's congestion, right? And then you keep sending. Right, so before we move on, any question about this behavior? So basically, this is describing what this is talking about, right? And the key is what happens after timeout, okay? So, this TCP version, as I said, is a very, very early called TCP Cajo, right? So it's not really what we use today, okay? Because it's still too slow. Think about it, right? So each time you have a congestion, it's like a hammer you down to it's almost 0, right? 1, okay? Each time you find some condition, you hammer you down, okay? So this is not a desired behavior, right? But this is the TCP Tahoe, it's the original version of TCP, which actually works by that time, right? But think about the TCP has been invented for a very long time. There must be some variants, right? Evolved, okay? So, in early days, the truly popular variant is called TCP Reno, okay? Tahoe features are still there, but it has 2 additional behaviors, right? So the first is called fast retransmit, okay? Fast retransmit. The second is called fast recovery. So we will go through what is fast retransmit, what is fast recovery in the next few slides, okay? So keep in mind, we are now in an advanced version, not TCP Tahoe, it's a TCP Reno, okay? So what is fast retransmit, right? So if you look at the Tahoe, what's the problem, right? So if you have a segment loss, right? So there's a long wait until the timeout, right? So because before you timeout, you have to be waiting there, right? So Reno actually has an optimization. Actually, I mentioned that a long time ago, right? If you remember last lecture, right? So you can retransmit after 3 duplicate ECKs. Right? So let's just look at it, right? So let's assume packet 4 is lost, okay? Packet 4 is, okay, sorry. Yeah, I use the wrong screen. So packet 4 is lost. So you will not get a acknowledge 4, right? So what will happen? By the way, so this number may be a little confusing. This is sequence number, right? If you have sequence number on this direction 1, then back will confirm 2, but it means the next should be 2. Okay, don't get confused. Let's just look at the number really on the blue arrow. Okay, this is acknowledge everything before 4 is done. Okay, but now because it's missed, right? So 5 will acknowledge still 4, right? Because anything before 4 is done. 4 is not done. Okay, I have to repeat this, and I have to repeat this. Okay, right. And after this one, okay, there's 3 duplicate. Right? So if you look at this is this is not duplicate, right? This is the first duplicate, second duplicate, third duplicate. Now we have some duplicates, right? This is 3 duplicate is acknowledgement. What we'll do is we know that packet 4 is lost. Okay, then we will immediately retransmit. Okay? We don't wait, because if you wait, it will be twice the. Let's say this is round trip time. Okay, right. Let's say this is your round trip time. This is your round trip time. Okay, right. But you need to wait twice. Right. So here because the scale is a little bit crazy, right? So actually, this between packets, it's really fast. Okay, it's depending on your bandwidth, right? How many bits per second. So this is way smaller than this thing. Okay, so if it's twice, it's a really long time than you. Now what we can do, hey, we find 3, 4. There's already 4, there must be something missing, right? Otherwise, it gives you one chance to acknowledge, move forward, right? And not move forward, not move forward, not move forward. Hey, I know that there's a packet loss. I will just do retransmit instead of waiting for twice the RTT, okay? So this is called a fast retransmit, right? And as soon as you get 3 duplicate acknowledgements, you retransmit. You don't wait for the timeout, okay? So this is pretty good because whenever you have a packet loss, right, you're surely, unless your window is really small, right, even if you have at least 4 packets, you will surely get 3 duplicates, okay? And then you will retransmit immediately. You will really, most of the time, you are not waiting for the timeout, okay? The second is called fast recovery, right? So let's take a look at. So what's the problem with the original after fast retransmit, right, what we do, just like it before, okay? After retransmit, what we do is we set the window size to be, previously we set window size, we hammer it down, we hammer to 0, okay? But that's too much, right? So this is what we discussed earlier. But don't reset to 1, okay? Let's do a fast retransmit. We just set the window size to threshold by half, okay? So this is, because we previous stage, we have a slow start stage. So this purpose of this is to avoid unnecessary to slow start, right? So you immediately get to where your slow start stops, okay? Well, we think it should be SS threshold, right? But if, unfortunately, this is SS threshold is too much overestimate, right, of this. But that's only at the beginning, you think about it, right? So next round, this SS threshold is half of the previous congestion, right? It will adjust. So starting from later, actually it's half of the congestion level, okay? Instead of the initial receiver window, additive type window, right? So you can see in the long run, actually it's only dependent on the previous, congestion window size, okay? Instead of the receiver window size. Okay? Initially you have no reference, you have to use the receiver window size. And so, this avoids slow start because where your slow starter achieves is really recover your window size to be half of the previous congestion window size. Right? You just skip this slow start step. Right? This will prevent expensive timeouts. So, because, if you, let me see. Yeah, if you, what is it? This. This, I think it's timeouts actually because of the fast retransmit. So, yeah, I'm kind of lost on this point. So if you know this, you just let me know. Okay. But anyway, it's really just to skip the slow start stage, just to reach to half of the previous condition. Right? So this is the desired performance. Okay. And but there's one thing, right? So we still need to hammer our window down to 1. Okay, still need to do. If timeout happens, okay, if it's it's timeout happens, so there are basically two cases. One is fast retransmit. One is timeout. Right? Fast retransmit is, if you remember, fast recovery built on the previous assumption that you have 3 duplicate transmissions. Okay, fast retransmit. But if it's actually, there's no fast retransmit, which usually happens if, let's say, so usually happens, it's not because just this is down, but also this is down, this is down, this is down, which means things are really bad, right? So the congestion level is super high, okay? It's not just a 1 down, but you recover quickly, okay? So if that happens, the congestion really bad, then you will not get any acknowledgement, right? So you have to wait for RTO, okay, launch time, timeout, okay? So in that case, means situation really bad, you need to hammer your window down to 1, okay? Well, situation not so bad, right? So maybe I just somehow lose a packet, but I can get the acknowledgement for later packets, right? Then I just hammer it down to half of the previous condition. Okay? So basically, if timeout happens, we still go back to slow start, right? Just like Tahoe. But if you, because there's no packet delivered, right? But if you still have some later packet delivered, but you missed the previous one, then you hammer it to half. Okay. So because the RTO really means the congestion really bad, right? So you should be safe, conservative. Okay, let's take a look at what the behavior is looking like, right? So in the Reno, we have fast retransmit, and if retransmission is triggered by fast retransmit, the fast recovery will not ham down to 0. Okay? So slow start happens here, and then you detect congestion like before, and timeout, and you hammer down to 0. Remember, timeout, so you hammer down to 0. But then because you go to 1, right, you need to do slow start. But after that, what you are doing is this, also congestion avoidance. You have some packet loss, but you keep receiving acknowledgement, right? So this is due to fast retransmit, not due to timeout, okay? And if this is the case, we hammer down to half, and we don't have this slow start, okay? And then we probe again, and then hammer down, and probe again, until where you have timeout, okay? And then you hammer down and try. So you can see that during this stage, right, We call this actually a so-called steady state, okay, where the congestion window oscillates around the optimal window size. Okay, let's just assume this ceiling is the same. Okay, right. Whenever you have some packet loss, this is where your congestion level is. Okay, your window size should be. So what Reno is doing is that if you don't have very severe packet loss, right? So you will always oscillating from half of this and this, right? Half of this and this, half of this, right? So we will have an assignment question, right? I mean the final exam question on this. Okay. So let's say your congestion level is really C, right? So the ceiling is C. Assume all the points are the same. Okay. It's not a big timeout. It's this level is the retransmission level, which means you have a reduplicated. Okay, and you keep having this, and it's stable. And what is this level? Who can tell me this number? The bottom. Any answer? This is C by 2, right? So because whenever you find this is a retransmit, fast retransmit, you hammer it to half of the previous windows. Okay. Then if you look at the bandwidth, right? So ideally you wanted a bandwidth that it's you can reach close to the level C, right? But what actually you do is you think about, right? Half of the area is wasted, half is utilized. So you are in the middle of this. Okay, it's like a 3 by 4. Okay, see, and again, maybe our final exam will have this question. Okay, just stay tuned. Right. Okay, any question about this? So you can see that it's not too bad, right? So you can utilize. It's in the steady state. Everyone can utilize 75% of what you can utilize. Okay, right. So it's not too bad, and this is only possible with a Reno. Okay, if you use a previous method, so they all hammer down to 0, and then this are totally wasted. Okay. Any questions? Right. So then let's continue. So Tahoe and the Reno are not the only variants, and so there are many variants which are also used in these days, okay, in your operating system. So Tahoe is the original method where we use slow start, right? Always use slow start, okay, hammer down to window size 1, right? And so another thing that it does is you did the timeout based on the RTT estimate, right? It's dynamic because if you remember, we have a moving average way of estimating the round trip time. Okay, whenever you receive something, acknowledge which packet you sent, you will estimate the round trip time. Okay, and then you have a moving average, right? Alpha R times the original value times 1 minus alpha R of the new round trip time. Okay, and then you twice RTT becomes the RT. Right? So this is still what Tahoe is doing. Okay? So they will dynamically adjust your timeout time according to your round trip time. Okay. Reno is what we just described, right? You have the 3 duplicate retransmit, and you have the fast recovery without slow start. Okay. And there's also the new Reno, right? TCP new Reno, and improve the fast retransmit. Right? So what it does is that each duplicated acknowledgement triggers a retransmit instead of waiting for 3. Right? So the Reno is safe, right? And the new Reno is aggressive. So it's actually not so good, right? So people don't think it's popular because if you have out of order packets, right? If you remember, we talked about the BGP protocol, right? Sometimes because of the link latency or bandwidth change, then the route will be out of order. Right? You will go this route, and then you go to another faster route, maybe for the next packet. So it will go out of order, right? So which means, let me see whether we can find a diagram. So which means this 4 is not really lost. Okay. This 4 is not really lost. It's just that the other takes the faster route, but this one somehow goes through a slow route and finally reach here. Okay, but you can still receive it if you keep this window there and keep acknowledge this, right? Selectively acknowledge these, and then when it's come, you can move the window here. Okay, but unfortunately, because I guess reduplicate, I will just retransmit, assuming this is not same. Okay, so this is a weakness. Right? If there's an out of order of more than 3 packets, then we are in trouble. So this is let me see where. So this is a little bit aggressive. Okay, I think it's not this slide. So this is not that popular. Okay, we also have VGAS, right? So VGAS is a delay-based congestion avoidance, right? So why we need a delay-based instead of, for example, RTO-based, right? So or acknowledge-based, right? So there's good reason, especially in wireless environment, you can either have packet loss or interference, and in that case, you cannot just rely on the acknowledgement. Okay, potentially it's not that level of congestion, but if there's a packet loss and you react aggressively, right, then so the actual bandwidth will become super rapidly. Okay, there are also many more variants. Okay, so what are the actual TCP versions that we are using in the real world? Right? So the problem is that nowadays we have very high so-called bandwidth delay product. Okay, in other words, so what it means that you think about every second you can put a lot of things here. Okay, right, and you think about this link as a pipe. Okay, and then from one side, like the west coast to east coast, right? So what happens is it will take some time to reach there, right? But then you think about how many data volume are here. Right? It's really your bandwidth, which means how tall this pipe is, right? And delay, how long this is. Okay, right? So this is basically every moment you have a lot of data that is moving around. Okay, right? So this is called a bandwidth delay product. Okay? If we have this basically this pipe, the volume is very high, right? So a lot of data. Then TCP actually performs poorly because whenever you hammer something down, right, including like say packet 4 is lost, then 5, 6, 7, 8, you ignore them. Right? You hammer to window 1 and retransmit. Right? So this is really severe, right? Because now it's potentially not just 5, 4, 4, 5, 6, 7. Right? You have a very big window because you can transmit in very high bandwidth. Okay. So then we need, for example, in Windows, now we use a so-called compound TCP protocol. Right? It is based on the Reno, right? So basically we have all these retransmission tricks, okay? But it also uses, two congestion windows instead of one, right? So one is also delay-based, okay? Remember previously we only use, delay to estimate the round trip time, and then we can set the RTO. Right? Now here we also have a congestion window that is delay-based, okay? Not just a packet loss. So there's a compound congestion control that based on both metrics decide whether we should do retransmit. Right, it's safer basically have another metric to help you. Okay, and in Linux, for example, right. So then your TCP version is called a TCP CUBIC. We will see what is TCP CUBIC later. Okay, it's really CUBIC is this fitting has a desirable property. We will see in detail in the later slide. So this is enhancement of the BIC, right, binary increased congestion control protocol, which I think we'll get into the details later. Okay, the window size is controlled by its CUBIC function. Okay, if you remember previously, our window size doubles each time in slow step. Okay, but when we reach the beyond the SS threshold, we do a linear function, right? So it's like exponential and then linear. But here we have a CUBIC function which also increases fast, but not that exponential. Right? But then we will not really go to linear, right? Because you still have the second half on the top that is slow. Okay? So CUBIC is try to solve this problem. Okay? And this window size is primed by the time since the last drop packet. Okay? And we will look at the example later. Okay, so firstly, let's look at what is high bandwidth delay product. Right? So this means the capacity of the network is large, right? So we talk about the bandwidth, which means how fast, like each time step. Let's do this. Here you have a pipe. So each time step, how many bits can you put on this? Okay, how many bits? This is very tall, basically, right? And the delay, round trip time, is also long. Right? So basically, width times height. Right? So this area is how many data are in your loop. And if you have a packet loss, you kind of cut out right in the middle, and whatever is after that packet, I have to do retransmit. Okay. So also, you can say, hey, both are large, right? The true reason is really, bandwidth delay product, right? The product's large, right? If you have super large bandwidth, but your delay is slow, that's a severe problem. Right? So this is really the amount of data that is in flight. Okay, how many data are in the pipe? Because you think about it, you have data in the pipe, right? You have data in the pipe, okay, before it lost somehow, okay, and 5, 6, you have lots of them. Okay? And all these are basically need to retransmit, right? Because for it lost, you acknowledge 3, 4, okay? All these are wasted, okay? So why does TCP perform poorly? The first reason is that the slow start, right? So the slow start and the additive increase are slow to converge, okay? Right? Because although you slow start to, let me see, your congestion level maybe here, right? But you have a slow start, you hammer to 0, and you need a stage to reach here, right? So this lots of bandwidth are wasted because your congestion can go to this level before congestion, right? And then you do a slow, you're half here, then you do a slow additive increase, something like that, until this level. So this thing is too slow. Right? By that time, you are using bandwidth only bit by bit. It's idle mostly for the other one, okay? So another thing is that the TCP is acknowledged, right? So an acknowledged clock, okay? So that means this is actually the key reason, okay? The TCP is acknowledged clock, which means your round trip time, right? TCP can only react as quickly as acknowledge are received. You think about it. For example, if 2 students are at UAB, right, this round trip time is really quick. Let's say, let's use some second, right? So in reality, it's orders maximum. Okay, 1 second. Okay. Then if there's one student in LA, this is in New York, right? So this may be 10 seconds. Okay. So, but TCP protocol is it doesn't care about it, right? So it's acknowledged. Just count how many duplicate, for example, 3 duplicate module, right? For these 2 students, you need to wait for example, 30 seconds, right? But for this student, only wait for 3 seconds, right? Okay, so the latency is totally different, okay, right? So TCP can only react to acknowledgement, but if you have a large round trip time, like here, right? So if you have 20-second round trip time, right? And then hey, I don't get a acknowledgement after 20 seconds, right? And then acknowledgement are delayed by itself. Okay, TCP itself will take 20 seconds to react. Okay, on the other hand, this will take just 2 seconds to react. If you have 3 duplicate and react, then it's 6. This will take 60. So that's unfair. Basically, the latency plays a part on how you will retransmit and react. Okay, especially for the 3 duplicate retransmit. Okay. And the question here. So the problem is that you don't want to hammer it down so much, because if you hammer it down too much, what will happen is that the bandwidth will be not fully utilized, right? Because so here's an example, right? If you have a bottleneck link, right, the bandwidth, it's high. Actually, the higher your bottleneck bandwidth, the lower your utilization rate, right? Almost half. Okay, the reason is very simple, because you keep hammering things down when you get to the congestion level, right? And if you have high bandwidth, you cannot fully utilize it. Right? Whenever you cut it down, there's a high, product of the bandwidth and the latency. Right? So then you waste a lot of things. Okay, by the time the utilization is going down. Okay. Similarly, if you think about so this is bandwidth, right? So how high the pipe is. This round trip delay is how long the pipe is, right? Similarly, if your pipe goes very long, latency, then the utilization also decreases. It can decrease to below 40%. It's really bad. So these things are not working out, right? So is there any way that we can avoid like a window being timed down and then slowly recover to the previous level, right? So we want a so-called fast window growth, right? Slow start and additive decrease are too slow, okay? By that time, maybe bandwidth is 10, but I'd be conservative, 1, 2, 3, 4, right? That's way too slow, okay? We want to converge more quickly. So this is one thing. The second is we want to maintain the fairness, right, with other TCP variants. Okay? I think there's a typo. And so the reason is very simple, right? So if you are being aggressive, right, finally, you still want to like if you remember that diagram, right? Let me see where it is. Yeah, here. Right. So it's, let's say this guy runs one protocol, this guy runs another protocol. We don't want the convergent status to shift towards any side. Okay, we want to still stay in the middle. Okay, right. But if you have some protocol that are more aggressive than others, right, it can push the line right to the other side. So one will occupy more bandwidth. Then this is not desirable, right? So we don't want that to happen. Okay. So this is basically, we want a fast window growth, but we still want a fairness, okay, for different TCP versions. If you remember, right? So we have Windows, Linux, they are running different versions. Okay. So we want them to still guarantee the fairness requirement. Okay. So window growth cannot be too aggressive. If one grows way more aggressive than the others, right, then it's not good. Okay. And we want also to improve RTT fairness, right? So the Tahoe Reno flows are not really fair, right? So the reason is because previously we assumed the RTT time is the same. Now we say, hey, some of them round trip is 2 seconds, another is 20 seconds. Then in that case, it's actually not fair, right? Because like two people from East Coast and West Coast, they react much slower than you. Okay, if you are faster, of course you can push the bandwidth higher. Okay, you are reacting higher. You think about, say, hammer to 0 and then slowly recover and then hammer to 0, right? But you are doing something like hammer to 0 and quickly recover, right? Hammer to 0 quickly. If you look at the area here, right, it's going to be larger than the other people who are using. Okay, so it's not fair. Okay? So we still want a fairness, and we want the implementation to be simple because a lot of these things are in the kernel layer, right? You don't want to run very slow. Okay, it's in the kernel space, not user space, and often with the hardware support. So how about the So one way to avoid this round trip time issue is using so-called compound TCP implementation, right? So like in Windows. Right? So this key idea is that we split the congestion window into 2 separate windows. Okay, one is a loss-based window, like the packet loss trigger, right? Acknowledge when you do not receive timeout. Okay, another is a delay-based window. Okay, so we want to compensate congestion window because the congestion window is unfair, right? Because acknowledgement is not considering you take 20 seconds to get back the acknowledgement, right? While the other guys take 2 seconds. So now you need to compensate for that, right? So you need to add a delay window, okay? You need to add this delay window. So after this operation, then things get much better, right? So congestion window is still following AIND, right? But you have a delay window. If your delay is 20 seconds, you add that window much better, right? So for example, previously we say, you are reacting. Oops. You are reacting super fast, right? The other person is after hammering down reaction slow, right? So, but that's fine because hey, this fast one will only +1. This guy only +2 round trip, right? So because this window is much larger, +20. So this will boost up so that the fairness is still encouraged. Okay, still encourage fairness by adding this D window, okay, delay window. So what are the rules for adjusting the delay window? Right. So if round trip time is increasing, then you should decrease the window. If the round trip time is decreasing, you should, increase the window, right? So because, let me see. So basically, the increase and decrease, you should, according to what you last time received, the round trip time, right? You should adjust the window size, right? So if you're having some round trip time, that potentially means, so if your round trip time is increasing, right? So yeah, so what I mentioned previously is wrong. So you are not just looking at 20 seconds or 2 seconds. What you're looking at is the rate of the change, right? So are you increasing from 20 seconds to 21 seconds, right? This is what it's talking about. Okay, if you are increasing, then your window should decrease. Okay, right? Because there's more congestion, right? So you should you slow it down. Okay? On the other hand, if the 20 seconds become 19 seconds, right? then yeah, so round trip time is decreasing from 20 to 19, then we can increase the window, okay? Because we can send more. Right? So this actually is adjusted based on what the rate of change of the round trip time, okay? Not absolute round trip time, okay? But by having the rate change, right, so it will guarantee the fairness. And also, you are also much better, right? So because this window is originally half of the ceiling, right? But this is not a hammer down, okay? It's actually much more, change is really very, very, it's a real-time change, okay? So let's look at a diagram showing what it means. So initially, you have a slow start for the congestion window, and you have timeout, right? And then you have a slow start, okay? But then you find, hey, right, so round trip time is increased, right? So then, you should, you should have a slower window growth, right? Because if you look at what we did here, right? If you have a, RTT is increasing, then you decrease the window size, right? So your slope is lower than even, 1, okay? And then if you find, hey, there's no problem, right? The round trip time is stable. Now you recover to, because this time there's no change, so this window size is stable, and this change. This change is using AIMD, right? Then you increase. Then you increase again, right? And then this time you find, hey, this is a retransmission, right? 3D prediction. This time you find, hey, now the round trip time is low, right? So it decreases suddenly. So what you can do is you can go beyond the slope of 1. You can send it even faster, okay? And if there's a transmission, so this slope is more than the 45 degrees, okay? And then you can have a timeout, you hammer down to 0 and a 1 and then slow start. So this basically allows you to use the round trip time to adjust how fast you send, right? So you can see if you look at the utilization, this is improved, okay? You can see this missing volume here is very small, right? So this aggressively responds to the change in the round trip time, and the advantage is the fast runtime, right? So immediately go to very high level. You don't go hammer down to here, okay? And small fair flows with different round trip time, right? Because basically round trip time is changing in real time, and you are also adjusting how fast you can send in real time, okay? So the problem is, again, you have to estimate the round trip time. Right? So this is very challenging, right? Because, we are estimating the round trip time change, right? So you need to know the previous is 20 seconds, now it's 19 seconds, right? So yeah, so this is the relatively challenge, okay? Another method, this is in Linux, right? So called TCP CUBIC. Right? So what it does is using a function like this, okay, like this. So the details of this function is not that important, right? So there's some parameter, right? So let's look at some trend of this function. Okay? Firstly, C is a scaling factor, right? And then beta is here, right? As a constant factor for multiple decrease. Okay, so basically what we are saying is think about it, right? So so firstly we should look at this, right? So the C window max, right? This is the window last packet drop. So you cannot go beyond that level because that's the level that you are surely in congestion. Okay. So then what we can do is we basically want to minus some portion from here. Okay. So this is like we first have this budget, but we want to minus some portion. But we are not minus it aggressively, like hammer down to 1. Right? It's a it's a quadratic function to look at to the time. Okay. if you expand it, right? So it doesn't matter how this thing is here, right? It's constant. Okay, let's don't pay too much attention to it here. But look at this, expand these two terms. This will be T cubic, right? And then you have some. So the cubic function is something like, let's go to the next one. Okay. So this function is carefully engineered, by the way. Okay. So let's consider TCP CUBIC example. Right? So you slow start and timeout, and then you hammer down. Okay, and then you know that previous congestion level is C window max, congestion window max. Okay, and then what you do is that you know this is the cubic function. Right? So you quickly go very close to So firstly, this thing is really fast. Okay? This is a cubic function. The cubic function is something that if you have a 0, then you have 3 roots. That's something. Okay. Using this cubic function, you can quickly close the gap to the previous level. Okay. That's how this is engineered. Okay. Basically, you will get infinitely close to here because it's a negative number. But again, so the idea is very simple, right? You quickly increase, even faster than the other way around, right? So slow. Okay. But then when you get close, you are even slower than the linear increase. Okay. So that's the cubic thing, right? So the slope is changing significantly, right? You have one slope change, then another slope change, and then maybe another slope change. So this is fast ramp up. And then when you get close, you really increase it really conservatively, even less than one at a time. Okay? And when you get to the previous level, right, slowly accelerate to probe for the bandwidth. Okay? When you get here, you slow down, but if you can reach here, right, which means the previous congestion is gone. Right? So what you will do is, remember this cubic function, it will go up again. Okay? Because this is probably a root if you think about this one. Okay? And then this cubic function will finally, if you increase to the previous level, you slow down, but then if you go past, you increase again, and then you will have what you have the congestion, right? You have a packet loss. Right? And what you do is you have this function again, right? And this time, right, you didn't go cross that, right? And the congestion happens. Hammer down and do right? So you can see this is pretty fast, okay? And then if you can go back beyond the previous threshold, you increase fast. Okay? So this basically says, when I get close to the previous threshold, I will slow down. Right? So this is very good. Okay. Let me see the time. Okay, so that's the time for today. We still have a few slides. We will continue next month. Right? Any questions? Let me see the chat. Yeah, today's lab is optional because some students have questions about the previous lab, so the TA decided to give some additional explanations. Okay, but you don't have to go there if you have no problem with the lab. It's okay. Any other questions? You're welcome. I don't see any other questions, and in that case, I will end this class and I will upload this video, okay, today. And have a nice weekend and see you on Monday. Thank you.